will be divided into two parts. So there will be 25 minutes of talk and then a 10-minute break and then another 25 minutes. And during the talk, if you have any questions, just like before, you can feel free to put your questions in the chat, either publicly, or you can also like privately message them to me if you want them to be anonymous. In particular, I just want to mention that we really strongly encourage questions from students because Bad Math Day is meant to be for you. So there's no bad questions. And yeah, so feel free to ask any questions that you have in the chat. And I guess, yeah, I think we can get started now. So yes, only bad math questions. Thank you, Max. So our next speaker will be Nikhil Srivastava from UC Berkeley, and he'll be telling us about a spectral approach to polytope diameter. So whenever you're ready.
Oh, thanks a lot, Marielle, and thanks very much to the organizers for inviting me. It's my first Bad Math Day. It's also my first time talking about this work. So this is a joint work with Hariharan Narayanan, who's at TIFR Mumbai, and Rikhav Shah, who's a student at UC Berkeley. And it's a talk relating discrete geometry, spectral graph theory, and I guess convex geometry. The talk will be divided into three parts. So first, I'll set up the problem I'm interested in, which is diameter of polytopes, which is a combinatorics problem. Then I'll tell you about the technique from spectral graph theory that we use to attack this problem. Then we'll have a break, and then I'll tell you how we use some ideas from convex geometry to put these two things together. So the talk is about polytopes. So what's a polytope? So I'm going to consider a set P, a subset of RD, which is defined by linear inequalities. So it's a set of vectors X so that AX is less than or equal to B. And I'm going to assume B is strictly positive. So in particular, this implies that the origin is contained in this set. And assuming the set is bounded, this is a convex polytope containing the origin. So the two important parameters in this talk are going to be the dimension D and the number of constraints M, which is the number of rows of the matrix A, which is an M by D matrix. So given such a polytope, we can study its combinatorial structure, and one of the most basic ways to do that is to look at its vertices and edges. So I'm going to define a point on the boundary of the polytope to be a vertex if some D constraints are tight at that point. And I'm going to define a maximal line segment contained on the boundary to be an edge if some D minus 1 constraints are tight on the line segment, and I'll require it to be a maximal line segment. So here's an example of a polytope. It's just the unit cube. The constraints are just plus minus the standard basis vectors. So I've written previously, I wrote it as AX less than or equal to B, but you can also just write it as the set of X so that X inner product AJ is less than or equal to BJ for some constraints, for some vectors AJ that are the rows of A. So in this case, those are just plus or minus the standard basis vectors. The vertices, so I've plotted a cube in 3 dimensions. The vertices are just, okay, so the dots and the edges are the lines containing these dots. So any questions about these basic definitions of a polytope, a vertex, or an edge? Okay. So
are we assuming that the description AX less than or equal to B is as optimal as it can be, as in there are no redundant rows?
No, sure. Let's assume that. Yeah. Okay. Yeah, you're right. Let's assume that. Otherwise, the D constraints wouldn't make sense. Okay. Yeah. Let's assume there are no redundant rows. Thanks. Okay. So given a polytope, in particular, what this means is you have these vertices and edges, but these now define an undirected graph, right? So if you just view the vertices as vertices of a graph and the edges as just, pairs of vertices, you get an undirected graph that I'm going to call G sub P, which is the one skeleton of this polytope. And what we're going to be interested in is this one skeleton. So so the number of vertices of this one skeleton is the number of vertices of the polytope. So the main question we're interested in is this: given a polytope in d dimensions with m constraints that are not redundant, how large can the diameter of the one skeleton possibly be? So by diameter, I mean in the sense of graph diameter. So the maximum shortest path between two vertices in the graph, GP. How large can this be as a function of m and d? And this is motivated by linear programming, where if you run the simplex algorithm, you want to maximize some linear function on a polytope, you move along this one skeleton, and the number of steps is bounded, well, is related to this number, the diameter. And so this picture here, this is some polytope, and I've drawn, or I stole this picture from Daniel Darouche, who has drawn its skeleton, and in the simplex algorithm, you're taking a walk along the skeleton. And so this is what's shown here is some path between two vertices in the skeleton. We want to understand how long these can possibly be. So there's a trivial bound, which is, well, the diameter is at most m choose d, because that's the trivial upper bound on the number of vertices. And that's exponential in d, so that's a very large bound. It's not very useful, but that's sort of a bound, some bound to give you some idea of what kind of numbers we're going to look at. And so, okay, so this is the question, and this is an old question going back to at least the 50s. And a guiding question in this area is a famous conjecture of Hersh from 1957, which is actually the diameter should be much smaller than the number of vertices. So the what used to be called the Hersh conjecture is that the diameter of GP, this one skeleton, is at most m minus d, where m is the number of constraints and d is the dimension of the polytope. So this was, well, open for a very long time, and there are many results about it. I'll just say some of the landmark results. So one important result is the theorem of Kalai and Kleitman from 1992, who proved that the diameter is at most m minus d to the log d. Okay, so that's much better than m to the d, which was the trivial bound we saw earlier. It's also much worse than m minus d. It's not polynomial in d. It's not a polynomial in m and d, right? It's m to the log d, quasi-polynomial. This is a beautiful paper, by the way. This proof is like less than a page long. I highly encourage anyone who hasn't seen it to look at it. And I should say that over the decades, there were some small improvements to this result, to this Kalai-Kleitman result, but this is the ballpark best that is known for general polytopes. Nothing better than this is known even now. So there's a big gap between the upper and lower bounds. Or between the conjectured upper bound and the known upper bound. And another very important result is this famous result of Santos from 2012, where he disproved the Hersh conjecture. So he proved the following, that there's some constant epsilon and an infinite family of polytopes with dimension going to infinity, such that the diameters of their skeleta are at least 1 plus epsilon times m. Okay. So this disproves m minus d, right? But it's still very far from this upper bound, right? The lower bound is linear, the upper bound is quasi-polynomial. And so, and this picture that's shown here, these are the bad polytopes that Santos constructed. They're called spindles. And the feature that they have that's kind of counterintuitive is somehow using not too many constraints, you're able to define lots of tiny edges, and that blows up the diameter of the skeleton. So these are sort of the highlights of what's known about this problem in the worst case. And it's still what's now, the sort of guiding conjecture in this field is what's called the polynomial Hersh conjecture written below, which is that, well, can you just prove that the diameter is some polynomial in m and d, some fixed polynomial? And that's still open. So any questions about this summary of the status of this conjecture?
I have a question.
Mm-hmm.
So are there, from the picture, it looks like there's already counterexamples in dimension 3. Is that right? Okay, so you don't have to go up really high.
Well, okay. So this picture is I think a projection of the smallest counterexample, which is in dimension 5.
Ah, okay.
And what Santos does in his paper is a lot of the work is finding this counterexample in dimension 5, which I think has 43 constraints or something like that. But then there's some like inductive way to boost that into an infinite family. So really, indeed, the core is to find this example in dimension 5. So I don't actually know exactly what this picture is. This is a picture in dimension 3, and it probably doesn't violate the Hersh conjecture because the Hersh conjecture is true in dimension 3. But it's supposed to convey the idea of the construction.
I see. Thanks.
So is the conjecture true in dimension 4, but it's not in 5 or above?
I think so. I don't know. I think some people in the audience may know better than me. It is true in dimension 3. I don't know what the status of dimension 4 is. Does anybody know? Okay, so that's the general Hersh conjecture. And this is still sort of quite open. Oh, somebody's saying they thought the counterexample was 43 dimensional. Okay, you're probably right. I said 43 was the number of constraints. Maybe that's the dimension. Yeah, it's some constant dimensional example. Okay, 43 dimensional, 86 facet. My mistake. In that case, I don't know. Is the Hersh conjecture true in dimension 5? Does anybody know? Oh, okay. So I take it back. It is true in dimension 5. Maybe known up to dimension 6 is what somebody is saying in the chat. So yeah, thanks a lot. Okay. But anyway, the general asymptotic version is this is what's known. Okay, so before I tell you the results, I want to mention another line of work, which is to study a slightly easier problem, which is given a polytope now specified with an integer matrix of constraints. So A now has integer entries, and so does B. The question is, can you prove a bound on the diameter of the skeleton of the polytope in terms of the dimension, the number of constraints, and this parameter delta, which depends on the size of the integers appearing in the description of the polytope. And so it turns out it's natural to use delta being the maximum determinant of a submatrix of A. Okay, so this is a measure of how big are the numbers being used to define the polytope. And this is sort of an easier question, right? That if I also tell you that these numbers are kind of small, can you prove a bound on the diameter of the polytope? And the first result in this line was due to Dyer and Fries from 1994, and they showed that if this delta is 1, so which means the matrix is unimodular, then indeed the polynomial Hersh type bound is true. The diameter is some polynomial in M and D. I think it's raised to the 13 or something like that. So it's a very explicit number. And then there were several intermediate works, and the latest result in this line is this result of Dadouche and Hanle, who proved that the diameter of a polytope is actually at most d cubed times this delta squared. So if you have a polytope which is defined using a matrix whose determinants are all small, then the diameter has to be small, d cubed times delta squared. And the result I'm going to talk about today is a slight improvement of this. It says under the same assumptions, you get a bound of d squared delta squared times some log factor. Okay. Now, this is not supposed to be a big deal. The result itself is slightly better than the previous results. The reason I want to talk about it is that it uses a new technique, which gives a very simple proof of this result. And I really wanted to give the simplest consequence of that technique. So I'm going to talk about this theorem. So any questions about? Yes.
Yeah, I have a question. So the determinant, like this, like I said, I'm assuming S and T can vary in size, right?
Correct.
Like from 1 to the whole thing. So why does it make sense to look at determinants of different matrices? I mean, they feel like they have different units. So you're taking max over different things.
Yeah, they do have different units. You're absolutely right. This is just sort of an artifact of how the literature evolved, because people are interested in unimodular matrices because determinant being 1 actually means something, that the inverse is integral. Mm-hmm. And then somehow that just became, I mean, they chose to parameterize the problem this way. Really, the only thing that matters is the maximum entries, the maximum 1 by 1 minors, which are the entries, and the maximum n minus 1 by, d minus 1 by d minus 1 minor. So okay. Really, you're right that this quantity is really capturing a couple of different quantities in one.
I see.
Yeah. Good question.
So if you just know these two quantities, like you just you have two numbers, just comparing the 1 times 1 and the n minus 1 times n minus 1, would you get sharper results?
Yeah, this delta squared is really delta 1 times delta like d minus 1.
I see.
Yeah.
Okay, sounds good.
Okay, so that's the statement of the theorem. So any questions about this statement? Any more questions? I'm sorry, whenever I said n, I should have said d. D is a dimension. Yeah. Okay, so we're going to prove this theorem using a sort of nice observation in spectral graph theory. So let me tell you what that is. So spectral graph theory is when you study graphs by doing linear algebra with their adjacency matrices. And what I'm going to use in this talk is a slightly generalized notion called a generalized adjacency matrix. So if you have a graph G on n vertices, then a symmetric matrix, symmetric real matrix, is going to be called a generalized adjacency matrix of the graph if for any off-diagonal entry Sij, it's non-zero if and only if there's an edge in the graph. Okay, so in the usual adjacency matrix, you put 1 if there's an edge in the graph. In this one, you're allowed to put anything, but it must be symmetric, and we don't care about the diagonals. So that's a generalized adjacency matrix. And I'm going to prove a little theorem, which I'm going to call theorem S for spectral, which relates the spectrum of any generalized adjacency matrix to the diameter of the graph, the combinatorial diameter of the graph. Okay. So here's the statement of the theorem. So suppose you have a generalized adjacency matrix S for a graph G. And suppose one of its eigenvalues is equal to 1 plus gamma, where gamma is positive, and all the other eigenvalues are contained in the unit interval. So of course the eigenvalues are real because it's symmetric. And so the picture is shown at the bottom of the slide. I have the real line. Lambda 1 is 1 plus gamma. And then all the other eigenvalues are sitting in this interval minus 1 to 1. That's the assumption, that you have a graph whose generalized adjacency matrix has this property. So this is called a spectral gap. It's the gap between the largest eigenvalue and the next one. Then the claim is the diameter of the graph is bounded by log of the number of vertices plus twice log of 1 over v min. So v min is the minimum absolute value of an entry of the eigenvector corresponding to this top eigenvalue. Okay, so right, all the eigenvalues have some real eigenvectors. I'm going to look at the one corresponding to the special eigenvalue lambda 1 and look at the minimum absolute value of one of its entries. So then the claim is the diameter is at most log n plus 2 log 1 over v min over square root gamma, where gamma is a spectral gap. So what this is saying is if you find a generalized adjacency matrix with a large spectral gap and somehow manage to control its top eigenvector, you will get a diameter bound.
Sorry, v min is taking defined using the sign or not?
Absolute value, minimum
Okay.
absolute value.
Okay.
So in particular, if one of the entries is 0, this doesn't give anything.
Yeah.
You need the top eigenvector to have all non-zero entries for this to be not vacuous.
But I can always scale the eigenvector, right? So what do you mean with eigenvector?
Unit vector. Sorry,
Okay,
unit vector.
Okay. Yeah.
Yeah. Okay. So minimum absolute value of an entry of v1 after it's scaled to be a unit vector. Okay. And I should say this is not really a new theorem. I mean, this is proven by Fan Chung in the 80s for adjacency matrices and generalized by Van Dam and Hamers in 95 for a slightly larger class. And it's essentially the same proof, but I'm just stating it this way. It works in this setting of generalized adjacency matrices. So any questions about the statement of theorem S? Okay, so I'm going to tell you the proof of theorem S. So this is the statement of the theorem. The proof is one slide. Okay, so the statement is you have this generalized adjacency matrix with a spectral gap. So the spectrum looks as shown here, and you want to bound on the diameter. So what's the proof? Well, okay. Wait a minute. Yeah. So the first step is to look at S to the K for some integer K, right? So you raise this generalized adjacency matrix to the K. And let's say you've diagonalized it. So the eigenvalues are lambda 1 through lambda n with corresponding unit eigenvectors, which is important, v1 through vn. So I've written it in this form. So by the spectral theorem, S to the K, sorry, there should be a to the K here. S to the k is lambda 1 to the k times v1 v1 transpose plus the same thing over the other eigenvalues. Okay. And now I'm going to use the spectral gap. Right. So the spectral gap tells me that all the lambda i's that are not equal to 1 are bounded by 1. And lambda 1 is 1 plus gamma, right? So that means entry-wise, this matrix is bigger than 1 plus gamma to the k times v1 v1 transpose minus n times the all ones matrix. Okay, so what facts am I using here? I'm using that the eigenvectors are normalized, so all their entries are bounded by 1, right? So this v1 v1 transpose, all the entries are bounded by 1. So I define J to be the all ones matrix. And then, this, I get that they're all bounded by J. And on the other hand, V1, I know its least entry is at least V min, right? So all of the entries of V1, V1 transpose are lower bounded by V min squared times the all ones matrix. And so I get this entry-wise bound that this S to the K is at least 1 plus gamma to the K times this V min squared times all ones matrix minus N times all ones matrix. So any questions so far? Okay. But now the point is that this is strictly positive for every entry if 1 plus gamma to the k times v min squared is strictly bigger than n, right? Because the first term dominates in every entry. So in particular, that means when k is log n plus log of 1 over v min squared over gamma, this whole matrix is strictly positive. Every entry is positive. So what I've discovered is that there's a somewhat low power of the generalized adjacency matrix, which has strictly positive entries. And now I'm done, right? Because, well, if the ij entry of S to the k is not zero, that means the distance between I and j in the graph is at most g. That's where I use that it's an adjacency matrix, right? The only non-zero entries correspond to edges. So if S to the k, the ij entry is not zero, it means there's a path of length k between I and j. So this gives me the diameter bound. The diameter is bounded by this log n plus log 1 over v min squared over gamma. Now, that's not what's written in the statement of the theorem, but any questions about what I just proved?
So it seems like you're taking the first step you take can be quite loose, but I guess you can compensate it by raising k to a larger power. So
exactly,
how loose is this general?
Excuse me?
So like taken all together, how tight or how loose is this bound?
I mean, this can be very loose. I mean, it really depends on how well that eigenvector is.
Yeah.
I mean, you have graphs where v min is exponentially small, so you can get very bad bounds on this.
Yeah.
Yeah. So I should say though that this doesn't prove the theorem, right? The theorem has a square root gamma. This has a gamma.
Right.
But the conceptual point is this spectral gap allows you to prove that a low power has all positive entries. Now, how do you get the square root gamma? Well, you do the sort of standard thing. You replace S to the k by a Chebyshev polynomial applied to S. Okay, so Chebyshev polynomial is, this orthogonal polynomial that maybe we all know. Tk of cosine theta is cosine of k theta. And it has the property that it's bounded in the unit interval by 1 by the formula written because it's a cosine. And it blows up very rapidly outside this interval. So if you replace the polynomial x to the k by Chebyshev everywhere here, and the same proof works actually, right? Because the spectral mapping still works. So tk of s is tk of lambda 1 plus, summation over tk of lambda I, blah, blah, blah. You get the same thing, but you pick up a square root because this blows up faster than a monomial. So you literally get the same theorem with a square root. Right? Because now I've exhibited, again, a polynomial of S, which is everywhere non-zero, but then the diameter is bounded by the degree of that polynomial. So that's the proof of theorem S. So any questions about the proof of theorem S?
Nikhil, can I ask, are you using somehow that the entries of this first eigenvector V1 are non-negative when you do this first inequality?
Yes. Okay, you're right. You're right. Okay. That's a good point. I am using that. Okay. So yeah, I should throw in one more assumption that all the off-diagonal entries have the same sign. Thank you. Yeah. So I should. You're right. So I used in this proof that V1 transpose is bigger entry wise than V min squared times J, and for that I would need all the entries of V1 to have the same sign. And so you're right. I should add one more assumption to this theorem, which is that all the off diagonal entries are the same sign. And then by Perron-Frobenius, V1 is positive and it works out. Thank you. Yeah.
I see. Thanks.
Mm-hmm. And yeah, of course, there should be a to the K. I mean, yeah, okay. But yeah. Any more questions about this?
So is the distance between the two vertices the same thing as the diameter, like the minimum of the...
Right. That's right. Because in this bottom statement, we're proving that for all I and j, the distance is bounded by k, right? For every pair I and j. So that means the maximum distance is bounded by k in this case.
Oh, so diameter is the max. Oh, okay. Yeah. Okay.
Oh, yeah. So I should define it. This is the maximum over vertices I and j in the graph of the distance in the graph between I and j. Sorry, maybe I should have explicitly defined it. That's the graph diameter. And here I've proved that for every I and j in the graph, this happens. So therefore, the graph diameter is bounded by k.
Okay, thanks.
Yep.
How do you go from tk of s having non-zero entries to distance less than equal to k? Because in the power case, it's very clear, but now you have cancellation possibly.
Right. So you may have cancellations, but you can never create entries between a pair of vertices that's at distance greater than if you have a polynomial of degree k, right? Then it is still true that every non-zero entry in tk of s comes from a path of length at most k. So cancellations will only create zeros, right? They'll never create non-zeros.
Mm-hmm. Yeah.
Yep. Any more questions? That's the end of the first part of the talk, by the way. So in the next part, I'll use this to say something about polytopes.
So if there's no more questions right now, why don't we take our stretch break? So we'll come back at, shoot, I have to convert the time.